So we're going to take a look at rates of change today. And good morning, Sage. And the stuff we're looking at related to rates of change, we're now in chapter 3. Hang on a sec, my chat has disappeared from the screen again. Why does it go back there? All right, back to gonna need a browser and the whiteboard. All right. And right now we're looking at section 3.1, and with respect to rates of change, 3.1 is about establishing what is this idea that in calculus we call the derivative. And this word was co-opted by the math community a couple hundred years ago, maybe 300 years ago. No, let's see, 250 years ago, somewhere in there. Anyway, for use in calculus, and it's related to rate of change. Now, rate of change on its all generally refers to, it's synonymous with average rate of change. Which is just slope, right? Talked about that before. So we've got this idea that we have these points, and there's a second y value and there's a first y value. And related to that second y value is a second x value and then a first x value. And when we take the difference, right, so that's the change part, y2 minus y1 and x2 minus y1, and then we divide them, that's the rate part, rates of change, this gives us the slope. If we use function notation, then we get something like f of x2 minus f of x1 divided by x2 minus x1, and hopefully you saw that pop up in a college algebra course once upon a time. So let's take a look at this graphically. So I have some curving curve, f of x here, and then we pick an x value over here. Let's say that's x1. And we pick another one over here, and that's our x2, and each of those lead to a point, and that point has a corresponding y value, right? y1 there, and y2 somewhere over here. And we calculate our rise, right? y2 minus y1, and our run, x2 minus x1. So we take that difference, that gives us the average rate of change between those two. And so let's try to draw a line in there to the best of my ability with this thing. Not too bad. Let's just move it a bit. Come here, there you go. All right, so there's my line. So the slope we have here and the line are related. The line's called a secant line. We talked about that a couple weeks ago. And then we also talked about moving one of these points toward the other. So like maybe I'm going to take x2 and slide it toward x1. Now the difference of these two is abbreviated a couple of different ways. So change in mathematics, remember, is that capital Greek delta. So the distance between x2 and x1, we could call that delta x. And so this change right here, we could call that delta y. Right? So I could say delta y, but it really means change in y. This one down here really means change in x down there. And so that's just another way to talk about that. Sometimes it's MSEC as a little subscript there for secant. And again, it's just change in y over change in x. Another way to think about it is this x1, let's just call that x there. And then if I add on that little change, then x2 becomes x plus delta x. And that's just this number right here, right? I started here at x, I added on that value delta x there. So x plus delta x gives me this other one. So sometimes we'll see this written in function notation as f of x plus delta x minus f of x for the numerator, divided by, well, these two, the difference between the x values, that's just delta x. So I'm just trying to get you used to this notation here. Oftentimes, instead of writing delta x, a lot of places call that h. So we'll see that in the homework, we'll see that in the book, and in other videos, sometimes that's just called h. So again, another form of this notation might look like this. Oops, using h this time. So both h and delta x are just a small change in x. So h, sometimes referred to as delta x, is just a small change in x, small being relative. And so that's pretty straightforward. You guys have been playing around with slopes since you were early on in your algebra days many years ago. The trick here is to try and look at the idea called instantaneous rate of change, and that's kind of a problem. So I just want to mention a couple more things about rate of change, then we'll pick some algebra to work on. Again, rates of change. There are many things that change in the world around us. So for example, COVID-19 is a bit of trouble right now, and so we have infection rates that we have to worry about. Maybe you walked or drove or moved around your house, so we have speed, right? Speed is the idea of changing position, and so that's velocity also. I had a little bit of coffee this morning, and so that caffeine is a stimulant, but it doesn't last forever, and so there's the rate at which our body processes any kind of chemical, whether it be something like ibuprofen or caffeine or sugar. We have the rate that is metabolized by the body. So rate of, let's say, decay, decrease, let's go with decrease. Rate of decrease of substances in our blood. For example, I mentioned caffeine. Caffeine, I believe, has a half-life of about 6 hours. So that means every 6 hours, half of the caffeine. Consumption rate of snacks, yeah, no doubt. I've got some Cracker Jacks I'm going to snack on after class, right? How many Cracker Jack pieces do I eat per minute? So we have, yeah, there's tons of rates, right? If you think about it, you're going to find all kinds of rates out there. Rate of snacking, good one, like that. Populations rise and fall. So, you know, the population of Oregon goes up and down over time. In general, populations are increasing because we are reproducing faster than we are dying off. And then there's all these other factors like migration. But if we looked at like the world population, it's been steadily rising for a long time. So population change. Let's see. Oh, right. Related to gravity, speed, sorry, velocity, speed, gravity is what I was thinking about, right? We drop something, it falls. We jump, we come back down. So gravity is a good one. And we could spend all day just kind of listing up rates of change. Now the point of this is to say, well, when we find a rate of change, we work with 2 points, right? Rate of change involves 2 points. That is the way it's done. If you don't have 2 points, you don't have a rate of change. So 2 points of information are needed. So this brings up a bit of a conundrum when we try to find an instantaneous rate of change, a slope at a point. Right? How can we have slope at a single point? We have no change at a single point. We just have a spot. And that's where things get weird. And we started talking about like the philosophy of this idea and infinity a couple weeks ago. We got kind of weird, and it is weird. There's some weird ideas there. And the kind of cleverness that gets us around not having 2 points is we really look for patterns. So it's really that it's a pattern that we observe. Because we have this clever definition that we say, let's take the limit as that little bit of x, that change in x shrinks to 0 of our change in y. So that's my change in y with function notation divided by that change in x. And the key here, right, is we technically really don't let dx equal delta x equals 0. We just look to see what happens as it gets close to 0, right? This is as that delta x, that small change in x, approaches, but doesn't actually get to 0. So we kind of work our way around it by that. We say, we don't actually get to the single point. We just say, hey, it looks like this is the pattern, right? And we have a precise way to do that with that crazy precise definition of a limit, which is kind of mind-blowing. And we're really not going to do too much more with that except the basic linear stuff and those couple of quadratic problems we looked at. So let's give this a shot. So just a simple example. Let's go to f of x equals x squared, which we did before a couple weeks ago. And let's try x equals 1. Make it super easy there. So I'm just going to draw up the graph of that here in GeoGebra, and Desmos works just fine. I recommend function notation, so I'm typing f of x here equals x squared. And I'm interested in the point, so parentheses for point, 1 comma f of 1. GeoGebra does a nice job of adding the second parentheses for each. So here's my point of interest right there. And one reason I like GeoGebra is I can then add a point on the graph here. So I'm going to put a point, say right here. And then I'm going to draw a line. Where's my line tool? It's somewhere here. Line. That one. Click, click. Okay. So this is my secant line, and I can ask for the slope by hitting more, and then slope is hiding behind my tools here. Slope, and it says select the line. So I'm just going to click there. And let's zoom in. So I can just grab this point. Oh, not on the point tool. And I can see, is there a pattern as I move one point toward the other, and it's greater than 2 up here. As I move it toward A, it gets closer to 2. Let's blow this up a little. Oops, whoa, what happened there? I have to use the zoom tool now. No, I want. It's not doing what I want. All right, probably can't undo it. Sorry, technical difficulties. I want a bigger font. Let's try that. There we go. And zooming in is not helpful here because I need to see that number. Come here. One of those days with technology. Oh, I want you, please. All right. So again, I am above 2 over here, but then when I get to A, the computer's like, cannot compute, I don't have 2 points, but on the other side, I can see I'm a little less than 2 as B approaches A, gets closer to 2. So we can explore this graphically. We've done that before, we're doing it again. We can do it in a table, and let's try it on paper now. So we're at the point x equals 1. And we need to find the slope. So the slope's going to be that x, f of 1 in this case, plus our delta x minus f of 1 divided by delta x. So this is our m secant. And so usually the way I approach this is it's kind of a 4-step process, right? I got to figure out, well, first, what is that thing algebraically? So that's like step 1. Step 2 is we do that subtraction because I got to clean up the numerator before I can divide. So step 3 would be doing that division. And the 4th step is to see if there's a limit. So let's do the algebra first. So what is f of 1 plus delta x? Well, function notation, you should think about it wherever there is an x, just have it be a parentheses instead. And then what goes into that parentheses is whatever you saw here. So if there's an, oops, I want to change color. There we go. If there's a 1 plus delta x in there, then in the parentheses for the function over here, there's going to be a 1 plus delta x, like that. And delta x is a single thing. They're not, the delta is not separable from the x. It just means, hey, this is a little change in x there. Well, to square this means to multiply it by itself. So that's 1 plus delta x times 1 plus delta x, which is going to give us 1 squared plus 1 delta x and another 1 delta x. So there'll be 2 delta x's and then plus delta x squared. And that's that. Then I get to subtract f of 1. Well, 1 squared is 1, so that was step 1 there. So step 2 is to do the subtraction. What happens when I subtract f of 1? Well, 1 plus 2 delta x plus delta x squared minus 1. That cleans up pretty nice. That's just going to be 2 delta x's plus the delta x squared. And then we get to divide that by delta x. So I'm going to come back up here. I've got 2 delta x's plus delta x squared over delta x. And we can factor delta x out of the numerator. That's going to cancel with the 1 in the bottom. And so we have a number divided by itself here, which is 1. And so the secant cleans up pretty nice. It's always going to be 2 plus whatever that change in x was. All right. And if we want, we could look at this in a spreadsheet to see that that actually happens. I think I do want to do that. Let's see, show desktop. Let's whip out a spreadsheet. Got one over here. And let's see, I'm not ready to do that one. Let's bring up a new one. All right, so we have x, and then we have f of x equals x squared. So I'll have, for example, we have the point 1, 1 we're considering, and then we're going to add on a delta x and see what happens. So we want to have the rate of change here, the secant slope. We'll calculate here, and I just want to make a note of what delta x is over here. So delta x. So let's start off with 0.01. And so over here, I'm just going to say, all right, take the x value above and add to it whatever I say delta x is. Oops, right there. And then for the function value, I just say equals, take whatever x value we have here and square it in this case. And then the slope over here, parentheses, is just, right, y2 minus y1 divided by, more parentheses, x2, oops, no, I totally did that wrong. y2 minus y1, there we go. Get the y's together. And then x2 minus x1. So here we can see just what the algebra showed us, that, hey, look, it's 2 plus delta x, right? 2 plus 0.01. And if I change that to like 0.5, then it should be 2 plus 0.5. And if I change this to 0.001, then it's 2.01. Now, delta x could go the other direction from the x value, so I could have a negative delta x. So negative 0.001 should be 2 plus negative 0.001, which is 1.999. So the smaller delta x gets, it looks like we're getting closer to 2. So if I go in here and sneak in a couple more zeros, right, I'm getting closer and closer to 2 for that slope. So that's the observation we're making. Back to the notes page. So putting it all together, if I want to find the slope of the tangent line, and a tangent line is different than a secant, it's the line that just touches at one point and has the same slope that the curve has, right? So M tangent, slope of tangent line at a point. And tangent line means at that point, the slope matches the curve. And so if we think about that, right, no matter how small delta x is, so if I am standing on the graph at this point right here, if I take the tiniest step up this curve here, it's going to be steeper than it was at that point I was at here. If I take the tiniest step backwards, it's going to be slightly less steep than where I'm at, right? So that no matter how small a step I take, there'll be a slightly different change in the slope from that point. So we're saying at that point, the slope is as close to 2 as you can get. And so that takes the idea of limits that we were talking about, seeing if there's a pattern. So in this case, the slope of the tangent line is the limit as delta x goes to 0 of r, what's called the difference quotient, the rate of change formula, that f of x plus delta x minus f of x over delta x. And for us, right, that cleaned up dramatically. Summarize the algebra on the other page, we just have 2 delta x. No, we don't. We have 2 plus delta x. That's what it cleaned up to in the end, once we cleaned all of that up. And as delta x goes to 0, this term right here is disappearing. I think it's 1s, 2p's maybe. So then we get just 2. The slope seems to be 2 there. And then we can graph it and see what it looks like just for fun. So let's turn off the secant here. Let's see. I want that to hide. I want that to hide. And I want that to go away. And so I'm just going to graph that line. Now, the easiest way to graph a tangent line, by the way, I guess I should write the algebra. So that's just the slope that we find. For the actual tangent line, the easiest thing to do is use the point slope formula for a line. And then you can clean it up if you want. So that would be y minus y1 equals m times parentheses x minus x1. So for us, plugging in the values, so we have, remember, x equals 1 here, and f of 1 is 1 squared, which is also 1. So that means we have at the point 1, 1. So plugging that in here, I get y minus 1 equals equals the tangent slope 2 times x minus 1. And I can just type that in as I see it, or I could clean it up. And then if we zoom in here, does it look like it just touches at that point and matches the slope without having more than one point? And you know, the more we zoom in, it looks like, yeah, looks like it just, that the green line seems to be above the blue one. The blue one is the tangent in this case. So can a tangent line cross through at that point? The answer is yes, but it doesn't here. The key of a tangent line is it matches the slope. Okay. All right, so let's try a more complicated one. How about, let's do another quadratic for fun, make sure we have the idea of how to do this. So we have two different options when we're